Real exam questions. This is question 42 and it deals with slab design and yield lines. Determine the top and bottom reinforcement of a square slab without taking into account the minimum and torsional reinforcement. The slab is loaded with 20 kN per square meter, the design value in ULS persistent. Concrete quality is 30 megapascal, steel quality 500 megapascal. The concrete cover is 30 millimeters. The depth of the slab is 200 millimeters. The size of the square slab is 6.4 meters. And the top bending moment is equal to half the bottom bending moment. With top bending moment, we mean the negative bending moments, and the bottom is the positive bending moments. First, we look at the axis of rotation, which is at the supports because it's fixed end support. So on the four sides, we have four axes of rotation. Then for the negative bending moments, we have the yield lines at the supports. And for the positive bending moments, when we have two rotation of axes which are crossing, then the yield line starts there. So in this picture will give us then the situation of the bottom bending reinforcement of bending or yield lines, the bottom yield lines, and the top yield lines, with the relation that m top is equal to m bottom divided by 2. The work done by the external forces is then 4 times, because we have 4 triangles, 4 times 6.4 times 3.2 divided by 2 times the load 20, and the mean deflection is delta over 3. So the work done by the external forces is 273.07 delta. Bear in mind that this is, of course, because those are all equal triangles, so you can find this much quicker by saying it's the total load divided by 3. The work done by the internal forces. First, let's start with the top bending moments, or the negative bending moments. We got 4 lines, 4 yield lines, so it's 4 times the top bending moment projected on the axis of rotation. So that means 6.4, and times the angle of rotation, which is of course delta divided by this distance, which is 3 over 2. There's this. And then we go for the positive bending moments. For instance, this is MB projected to the axis of rotation. So it is 6.4 times the angle of rotation, which is delta divided by 3.2. And we got that 4 times for this, and this. So D is then equal to 12 MB times delta, because we have substituted the MT equals MB divided by 2. E must be equal to D, and from that we can calculate MB, and or the positive maximum bending moment, and it is 22.76 kilonewton meter per meter. And the negative bending moment is half of it, so it's 11.38 kilonewton meter per meter. Now let's look at the reinforcement. We will say that on the top it's marked with a T, and the reinforcement in one direction, let's call it X direction, is on the first reinforcement layer, and the Y direction is the second reinforcement layer. So for the top, for the first layer of reinforcement, the effective depth is equal to total depth minus cover minus point of gravity of the reinforcement, but we don't know yet what the reinforcement is. So because it's a slab of 200, so we will just start with diameter 8. and then DHT is then 166 millimeters. The needed reinforcement is the bending moment on the top divided by the lever arm, 0.9 times 166 times the yield strength of the reinforcement. And this amount we multiply by 1.1 because we are using the upper bound method. That's why we have to use 1.1. And the needed reinforcement is 193 square millimeters per meter. Or you can convert it in diameter 8, center to center 260. You see, this is 8, that's okay. But if this was, for instance, not possible, and you have to go for diameter 10, then you redo the calculation with 10 until this and this number is the same. The second layer of reinforcement at the top in the other direction, the effective depth is the depth of the slab minus concrete cover minus the diameter of the first layer minus point of gravity of the second layer. Again, we assume 8 millimeters. We calculate the needed reinforcement at this yield line, and it's 202 square millimeters, or diameter 8 every 250 millimeters will be fine. Now let's have a look at the bottom reinforcement. We have the effective depth equal to 165. For the bottom reinforcement, the bending moment is bigger. So that's why we start with diameter 10. The needed reinforcement is then equal to 388 square millimeters, or diameter 10 every 200 millimeters. In the second layer at the bottom, the lever arm or the effective depth is then equal to 155 millimeters, and the needed reinforcement is equal to 413 square millimeters, or that's a diameter 10 every 190 millimeters. So now we make a summary of the total needed reinforcement. At the top, we had a yield, plastic bending moment of 11.38, needed reinforcement 193, and it's a diameter 8 every 260 millimeters. So this is your answer to this question.